Welcome to my YouTube channel. Today, I'm gonna talk about Gaussian elimination and low echelon form. For a non-xi and with arbitrarily given numbers ai and b, the equation like this is called the linear equation. And a collection of linear equations like this is called the linear system. How can I find the solutions of a linear system? Gaussian elimination. Today's our goal is, when a linear system is given, to find the solutions for the unknowns xi. Gaussian elimination we will learn today is one of the methods for solving a linear system. To understand Gaussian elimination, we first need the definitions of a couple of things. Now, this is an example of linear systems. The coefficient matrix of this linear system is the matrix containing the coefficients in the same arrangement like this. Also, the augmented matrix of this linear system is the matrix formed by attaching the numbers on the right side of the equations to the coefficient matrix. Sometimes we draw a line like this, and sometimes we don't. Now, let's define the elementary law operations. The following three actions are called elementary law operations. The first one is multiplying a law by a non-zero number, like the example. The second one is exchanging two laws, like the example. The third one is changing a law by subtracting a non-zero multiple of another law from it, like the example. These operations are important to solve a linear system because the theorem says these operations preserve the solution of linear system. So, we are free to use these operations on the augmented matrix as needed to find the solutions. Now, let's find an echelon matrix, which is also called an echelon form or a low echelon form. This is a matrix with the following properties. First, the original laws are at the bottom. Second, the leading entry of each non-zero law is in a column to the right of the leading entry of every law above it. Leading entry is the leftmost non-zero entry. Let me give you some examples. The example A is an echelon form. In an echelon form, a leading entry is called a pivot. So, the pivots of the example A are 2 and 3. And the number of the non-zero laws is called the length of the matrix. The length is not changed by an elementary law operation. The example B is not an echelon form. This is because the original laws, the second law, and the first law are not at the bottom. The example C is also not an echelon form. This is because the leading entry in the third law must be to the right of the leading entry in the second law. Using these definitions, if I explain Gaussian elimination, it will be called the method of finding the solutions of a linear system by expressing the augmented matrix of a linear system. And using elementary law operations, we express the matrix as an echelon matrix. An echelon matrix gives us the solutions. Now, let's solve a couple of examples using Gaussian elimination. There is a linear system. If the number of non-xi is greater than the number of equations, it's called underdetermined. If they are equal, it is called determined. And if there are fewer unknowns than equations, it's called overdetermined. In this case, since there are 3 unknowns and 3 equations, then this is determined linear system. Let's find the solutions of this linear system using Gaussian elimination. First, this is the augmented matrix of this linear system. Using the elementary law operation 3, change the second law by adding minus 3 times the first law to it. And change the third law by adding minus 1 times the first law to it. Then we obtain the following matrix. However, because the leading entry of the second law is not to the right of the leading entry of the third law, it is not an echelon form. And similarly, using the elementary law operation 3, change the third law by adding the second law to it. Then we can get echelon form. Expressing this matrix as linear equations, we have x1 plus 2x2 is equal to 2, minus x3 is equal to 2, and 0 is equal to 4. But since it does not make sense, there is no solution satisfying the linear system. We refer to a no-solution system as an inconstant system. A determined linear system usually has a unique solution, but not always. Now, let's look at another example. There is a linear system here. Because the number of unknowns is 4 and the number of equations is 3, then this system is underdetermined. Let's find the solutions of this linear system using Gaussian elimination. First, this is the augmented matrix. Using the elementary law operation 3, change the second law by adding 3 times the first law to it, and change the third law by adding minus 2 times the first law to it. Then we obtain the following matrix. And similarly, using the elementary law operation 3, change the third law by adding 2 times the second law to it. Then we can get an echelon form. Here, the pivots are 2, 1, and 11, and the pivot variables are x1, x2, and x4. So x3 is a free variable. Expressing the obtained echelon form as linear equations, we have 2x1 plus 3x2 minus 2x3 plus 4x4 is equal to 4, x2 plus 10x4 is equal to 13, and 11x4 is equal to 11. Simplifying these equations, we have x4 is equal to 1, x2 is equal to 3, and x1 is equal to x3 minus 9 over 2. The reason we expressed x1 by using x3 is because x3 is free variable. So they have infinitely many solutions, and the solutions are expressed like this by using a free variable. And because the solution exists, we refer to this linear system as a consistent system. An underdetermined linear system usually has infinitely many solutions, but not always. Now, let's look at another example. There is a linear system here. Because the number of unknowns is 3 and the number of equations is 4, then this system is overdetermined. Let's find the solutions of this linear system using Gaussian elimination. First, this is the augmented matrix. Using the elementary law operation 3, change the second law by adding minus 3 times the first law to it. Change the third law by adding minus 1 times the first law to it. And change the first law by adding minus 2 times the first law to it. Then we obtain the following matrix. Once again, using the elementary law operation 3, change the second law by adding the third law to it. And using the elementary law operation 2, swap the second law with the first law. Then we can get an echelon form. Expressing this matrix as linear system, we have x1 plus 2x2 is equal to 2, x2 minus 2x3 is equal to 5, and x3 is equal to minus 2. So this equation has a unique solution, 0, 1, minus 2. Because this linear system also has a solution, it is a constant system. An overdetermined linear system usually has no solution, but not always. Thank you for watching so far. If you have any questions, or if there is any topic you would like us to cover, Please let me know in the comments. Thank you.